In recent years, we humans have figured out a great deal about our universe. But that begs another question, which is very interesting and very controversial. Could there also be other universes? And do we have any evidence for this? Before we talk about other universes, parallel universes, let's remind ourselves what we mean by our universe first. Our universe does not mean everything that exists. It simply means the part of space from which light has had time to reach us so far during the 13.8 billion years since our Big Bang. So this is our universe. If space is bigger than that, then there are other universes, other regions of the same size farther away. If you want to know what's happening in the galaxy over here, you have to wait billions of years more for light to reach us. So we cannot see anything outside of our universe. One of the reasons this is so controversial is because many people say, oh, this is just stupid philosophical nonsense. You know, if we can never, by definition, see parallel universes, then it must mean it's not science. It's like talking about ghosts or something else that you can't see. But it's actually more interesting than this, because parallel universes are not a theory. They're a prediction from certain theories, which we can in turn test in various other ways. So to explain what I mean by this, let's look at another theory first. Einstein's theory of gravity, general relativity. It predicts a whole bunch of stuff which we can test and observe, like the motion of Mercury around the sun, the bending of light by stars, the time dilation that you can measure with your GPS and your phone, etc. And because of this, we take general relativity very seriously as a scientific theory, which means we have to take seriously everything it predicts, even things that it predicts that we cannot actually observe. Like what happens when you fall into a black hole. Einstein's theory of general relativity predicts exactly what happens inside black holes, but I cannot go observe it and then come and publish the results in a scientific journal here on Earth. It's impossible, right? But if one of my colleagues says, hey, Max, I don't like black holes, they can't just opt out of black holes. It's predicted by the theory. If they want to get rid of the black holes, they actually have to invent a different theory of gravity, another mathematical theory that's different from Einstein's, which doesn't have black holes, but which can explain everything else that Einstein did. And that has proven very hard, so hard that after 100 years or so of trying, many of the smartest people on the planet have failed to do that. The point here is that for a theory to be scientific, you don't have to be able to observe everything it predicts. You just have to be able to observe at least one thing that it predicts. And if that convinces you to believe in the theory, you have to also take seriously the other stuff it says. Now, what does this have to do with parallel universes? Well, first of all, we have a different theory, the theory of inflation in cosmology. It's also a scientific theory. It predicts a whole bunch of things we have tested and observed very carefully in the cosmic microwave background radiation and three-dimensional galaxy maps. It's right now the most popular theory in my field for what put the bang into our Big Bang. It was pioneered by Alan Guth and Andre Linde and others. It's a beautiful mathematical theory. And it also predicts parallel universes. In particular, it predicts that space itself isn't just really big, but that the space is actually bigger than our universe, maybe even infinitely big. So the logic is that if inflation theory is correct, and we take it seriously, we have to take seriously the idea that space is bigger than our universe, that there are parallel universes, other regions of space that are just too far away for us to see. I call these parallel universes the level 1 parallel universes because they're not that different from our universe. The only difference is that over there, the particles started out in different places, so the galaxies formed in different ways. And if there are people over there, they will still learn the same things in physics class, but they might learn different things in history class because things started out differently and history unfolded differently. A fascinating thing about parallel universes is that the most interesting question now really to me isn't whether there are any, but how many different kinds there are. This is the least controversial kind, the first level. Then there's level 2. And that's something that you end up with if you combine the theory of inflation with one more idea. If it turns out that string theory or loop quantum gravity or whatever the ultimate correct theory is going to be that unifies all of physics, if it turns out that that theory has more than one solution, with a homogeneous space in it, kind of like the equations for water, have three different solutions: liquid water, ice, and steam. Then this theory of inflation actually will create not just a big space, but it'll create a big space with each of these solutions actually happening. So the theory of inflation actually converts potentiality into reality. It'll make a universe with this kind of space, with that kind of space, with a third kind of space. Some string theorists think that there's 10 to the power 500 different kinds of space even. And what does it feel like to live in one of those parallel universes if they exist? Well, more interesting and diverse than in the level 1 kind, because they wouldn't only learn different things in history class, they would actually learn different things in physics class. They might learn, for example, that there are not 6 kinds of quarks, which is what I learned in physics class, but that there are 10 kinds of quarks, or 2 kinds of quarks. Many of the properties that we thought were fundamental properties of physics, according to string theory, are just telling you which particular solution of string theory you're in. Do these exist? We don't know, of course. How can we test it? Well, by testing inflation more and by studying string theory more to see if it seems to make any sense or not. If it does make sense, though, it actually would help answer another big mystery we have in physics, which is when you look around us in the world, our universe has all these numbers built into it that we call constants of physics. For example, there's a number that tells us how much dark energy there is. The value of the number is about 10 to the power minus 123. 0.000 blah, 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 1 with 123 zeros. And if you imagine that you could make your own universe, and you could have a little dial, a little knob that could change each of these numbers, I would recommend don't touch those knobs, because it turns out almost anything you change by a little bit will kill all life. If you put in more dark energy than we have by a lot, you destroy all the galaxies. Dark energy prevents them from forming, for example. If you change another number to do with the Higgs particle, suddenly you can't have any atoms. And this is a deep mystery in physics. Why is it that our universe has these numbers which seem to be fine-tuned for life? Is this just luck? Or is it some kind of miracle, or what? Well, the level 2 parallel universes actually give a scientific explanation for this. Steven Weinberg made a famous argument many years ago where he said that suppose the level 2 multiverse exists and the amount of dark energy is different in different parts of space. Then you predict something like the Sahara Desert. Most of it is dead, no life, no galaxies. But there will be still, some places where where the dark energy has exactly the right value to allow galaxies. And that's, of course, where we should expect to find ourselves. If I know that I'm a Bedouin and I live in the Sahara Desert, I'm not going to be surprised to know that I live in an oasis. That's the only places there are people really living. And it paints this picture where the same thing is happening on a larger scale in our cosmos. After this prediction was made, dark energy was discovered, and a Nobel Prize was given for it. And this has made people take this idea quite a bit more seriously. It's still fair to say that it's very controversial. We don't know, but it's certainly a scientific question we can discuss, whether our reality is this big. We should also be mindful that we humans have again and again made this mistake of underestimating the size of our cosmos. First we thought Earth was the center of everything, right? Then we discovered that our solar system existed in a galaxy and a universe. So it might very well happen again. There's no guarantee in the laws of physics that we humans should be able to see everything that exists. And if we cannot, by definition, there are parallel universes. Well, and there's even more. There's a third kind of parallel universes which have come into the scientific discussion from studying not the biggest things, but from studying the smallest things, by studying quantum mechanics, the rules that govern how atoms and elementary particles behave. This is arguably the most successful theory in all of science. It's given us transistors, computers, cell phones, lasers, etc. But at the cost of some weird ideas. Quantum mechanics tells us that little particles can be in several places at once. If the particles can be in several places at once, well, I'm made of these particles. I should be able to be in several places at once as well. And in 1957, a young graduate student named Hugh Everett worked this out really carefully and argued that what it really means is that there is a third kind of parallel universes, where when you make certain decisions, effectively our world splits into several parallel tracks. If I get a parking ticket, there's a parallel universe maybe where I didn't. But there's another parallel universe maybe where my car was stolen instead. So you win some, you lose some. This sounds very philosophical, but it's the way to test this, again, is not by speculating, but by studying quantum mechanics more. In particular, we should try to build quantum computers, which is a kind of machine which takes advantage of parallel computation and effectively using these parallel worlds. If we try to build them, and there are millions and millions of dollars spent right now to try to do so, if it fails, because we notice that the basic equation of quantum mechanics is wrong, then we can forget about all these parallel universes. But if they succeed, and they can calculate something in 5 minutes that would take longer than the age of our universe to do on a normal computer, I think that will make many scientists take these parallel universes more seriously.